All right, guys, today we're talking about rotational inertia. We're also going to look at the rotational version of Newton's second law. So, rotational inertia, or sometimes referred to as the moment of inertia, capital I, is an object's resistance to change in rotation, right? Just like mass and inertia was an object's resistance to change in motion, linear motion. Rotational inertia is the resistance to change in your spin or rotation. So with mass, it really didn't matter how the object was oriented, right? The mass is just the mass, how the collection of matter of that object. But for rotational inertia, the way that we distribute that mass is going to make a big difference. So for example, if I take my pen and I put my fingers in the middle and I try to rotate it, it's pretty easy for me to do that very quickly. But if I slide my fingers to the end of the pen and I try to rotate it, I'm not able to do it as quickly because more of the mass is distributed further away from the rotation axis. So the rotational inertia is higher in this orientation than it is in that orientation. Okay, and there's actually one more axis for this pen that has an even smaller moment of inertia. Can you imagine what that axis might be? Okay, so if I take my pen and I rotate it along an axis that goes right down the middle of the pen, kind of like a screw, that would be the smallest rotational inertia and the easiest to rotate because more of the mass is collected closer to the rotation axis. So that equation, sum of the mr squareds, we know that big Greek letter sigma just means sum for a collection of masses that are revolving around an external axis, then we'll just add up each mass times its distance to the axis squared. And this is the minimum distance to the axis. So minimum distance to the rotation axis. And then m is just each mass. So for example, in our solar system, we could determine the moment of inertia of our entire solar system by taking the mass of each planet and then multiplying by their distance to the sun squared, and then adding them up all together. For objects that are larger and they're rotating around an internal axis, so think of like a basketball that you can spin on your finger, that's going to be a little bit more difficult because the collection of masses will each mass kind of has a different distance to the rotation axis. So in order to calculate that moment of inertia, you would need calculus. And that's one of the things that you'll get to do next year if you take AP Physics C, using calculus to determine that moment of inertia. But for us in Physics 1, we can definitely determine that experimentally. We could apply different torques to the basketball, and we could determine the moment of inertia just by looking at how much it accelerates, okay? There are some moment of inertias that I would ask you to memorize. We don't do a lot of memorization in this course, but it will help you for the most part on the AP exam if there's an object given like a ring or a sphere or something like that. Typically, 99% of the time, they're just going to give you the moment of inertia, one of these equations. So if it's a sphere, it's 2/5 mr squared if it's rotating around its center. A rod, if it were rotating around its end, so that would kind of be like my pencil when I did it like this. And then maybe a rod when it's rotated through its center of mass, like that, is 1/12 ml squared. They're usually going to give you that equation. But it would help in the rare event that they don't give you that equation just to have these few memorized. So a ring, because all the mass on a ring is collected the same distance away from the center or the rotation axis. When we do the sum of the mr squareds, we just get the total mass times the radius squared. For the rod at the center, we end up with a coefficient of 1/12 times the mass times the length squared. And then when I rotate my pen about the end, and I get 1/3 ml squared. So 1/3 is bigger than 1/12. That is the moment of inertia around the edge of the pen is higher than the moment of inertia when I rotate it through the center. Okay, cylinders and discs are 1/2 mr squared, and spheres are 2/5 mr squared. For the basketball, I might consider that more like a hollow sphere because there's a lot of air inside, so that would be even different than the solid sphere 2/5 mr squared. But it might help you to memorize those. On rare occasions, you might need to have that memorized. Otherwise, they will typically give it to you on the exam. Okay, so can we look at a collection of masses? Can we determine the center of mass? And then let's imagine what is the rotational inertia if we were to rotate those masses around that center of mass. So for these two masses, I know the center of mass is going to be shifted more towards the 6 kilogram because it's heavier, and we know that center of mass is the average position of masses, so it's like a weighted average. So if I want to determine the position of the center of mass, which on my equation sheet says the sum of the MIXIs over the total mass, I'm just going to take each mass times its position divided by the total mass. But in order to give it a coordinate, I need a coordinate system. So I'll pick an origin, and I always like to pick one of the masses as my origin because that'll put the x coordinate of the 2 kilogram at 0. And then I'll add the 6 kilogram times its x coordinate, which in this coordinate system is 3 meters. And then I'll divide by the total mass, which is 8. So I've got 6 times 3 is 18 divided by 8. So that's what, 2 1/4. So 2.25 meters. So 1.5 would be right in the middle. So the center of mass is going to be somewhere over here. And what I'd like to do now is I'd like to determine the moment of inertia if these two masses were rotating around that center of mass. So we know the 2 kilogram is 2.25 meters to the rotation axis, and that leaves 0.75 meters for the distance to the 6 kilogram from the center of mass. Okay, so 2.25 for the 2 kilogram and 0.75 for the 6 kilogram. And if I want to determine the moment of inertia, I'm going to do the sum of the MR squareds, or I'm going to take each mass, so 2 kilogram, times its distance to the rotation axis squared, plus the 6 kilogram times its distance to the rotation axis squared. So we have 2 times 2.25 squared plus 6 times 0.75 squared. And I'm coming up with 13.5. And what would the unit be for moment of inertia? We know the unit for mass is kilogram. To get that unit, I'm really just going to look at the equation and do some dimensional analysis. We'll pick up a kilogram from mass, and then we'll pick up a meter from distance, but it's squared. So the unit for moment of inertia is kilogram meter squared. There's no short way to say that. We're just going to use kilogram meter squared each time. Okay? All right, the rotational version of Newton's second law, we use Newton's second law a lot, right? We know F net equals ma, and we know that if we can determine the net force, then we can calculate the acceleration, and then we can bring it over to kinematics. So acceleration was kind of our go-between between dynamics and kinematics. The same thing is going to happen for rotational motion. If I can come up with Newton's second law for rotation and torques, then I'll be able to get angular acceleration and apply rotational kinematics. So very similar to what we had done before. All I want to do is take any of my linear equations and just replace them, each variable, with its rotational analog. So torque is the rotational analog of force, right? Net forces cause accelerations, net torques cause angular acceleration. So I would say the net torque is equal to, well, mass is a measure of an object's inertia. So I'll replace that with moment of inertia for rotation, and linear or translational acceleration I'll replace with angular acceleration. So I come up with something that looks very similar to F net equals ma, and that is net torque equals I alpha. So I'll be able to do all the things that I had done with Newton's second law and apply to kinematics. I'll be able to do that in rotational as well. So I just need to determine the net torque, and I can determine the angular acceleration of a system. Okay, so what I'd like to do really quick is just kind of imagine a thought experiment, or if you want to go grab a roll of toilet paper or a paper towel roll, I want to imagine if I were to take the toilet paper roll and just drop it, versus if I hold on to one edge and I keep my hand still and I drop it and allow it to unwind or unravel as it falls. Which of those is going to hit the ground first? Okay, so go ahead and make a prediction before you try that. What I'd like to do on the next page is actually go through and see if we can determine the acceleration for both of these. Okay, in order to do that, anytime we have rotational motion, so imagine when I let go of this toilet paper roll and I hold on to one edge, it's going to unravel like this in a clockwise direction. So when I have rotation, I want to do not just a free body diagram, but also a torque diagram. So I'm going to do both. And the difference between a torque diagram and a free body diagram, a free body diagram, we just draw all the forces acting on a dot, which is considered the center of mass of the object. So we know that there's Fg, but there's also going to be a tension. And that tension is from me holding on to the rest of the paper there. So I'm going to call that an Ft. Now, the one thing I know is that this tension is going to be less than Fg, because I'm confident that when I release that roll of toilet paper, it's going to drop. It's going to accelerate downward. So I need a downward net force. And for the one that I just drop, I'm going to go ahead and put Fg only, and it should be clear from the free body diagram that the acceleration of the unraveling toilet paper is less than 10, the acceleration of the falling or the free falling toilet paper. What I want to do is actually get a relationship. What fraction of G are we going to get? And I'm going to do that by drawing a torque diagram. A torque diagram puts each of the forces from the free body diagram where they act, exactly where they act on the system. So I'll put Fg right at the center, and I'll put Ft right where the toilet paper is unraveling from. Okay, I could do a torque diagram for the free falling object, but because the force of gravity is applied to the center of mass, it's not causing a torque. It has no lever arm. So in terms of R times F, there is no R for Fg. So we get no torque on this one. That's why it's only translating. But for our unraveling toilet paper, we do have a clockwise torque caused by the force of tension. So what I want to do now is I want to set up Newton's second law for the rotational version. So torque is equal to I alpha. And the torque is caused only by tension acting at a distance of 1 radius away from the rotation axis. So my torque is Ft times R. And then my moment of inertia for something like a roll of toilet paper, I'm going to treat it like a cylinder. I know it's missing a hollow part there, but I'm going to go ahead and use 1/2 mr squared. And then I will relate that to the angular acceleration alpha. So that's my sum of torques. So that's the angular Newton's second law. And I'll also do the linear, the translational version, which would just be, mg minus tension, because I know mg is winning, and I'm subtracting tension, and that should be equal to ma. So what I have now is a system of equations with a few unknowns. But if you remember from the rotational kinematics, the rotation and the acceleration are related. So the acceleration of any point on the outer edge of this toilet paper roll as it unwinds is related to the angular acceleration. As it rotates faster and faster, we know that each piece on the edge is moving faster and faster. And the connection between the translational and the rotational is just the rotational times R, right? So if I do A is equal to alpha R, then I could replace alpha with A over R. So alpha is A over R, and it allows me to connect these two equations now that they have common unknowns. So tension, acceleration, and alpha, if I replace alpha with A over R, now I have a system of equations with just the same two unknowns. So I'm going to put in A over R. And then from the translational version of Newton's second law, I'm going to go ahead and solve for Ft. And I just get mg minus ma is equal to Ft. So I have a system of equations. I'm going to use this expression to substitute in to the other side. So for tension, I'm going to put in mg minus ma. Then I have times r, the lever arm, is equal to 1/2 mr squared times A over R. And I'm going to go ahead and start canceling some things. This R on the bottom would cancel with one of those. And then I have one R left over, which would cancel with the R on the other side. Okay, so I have mg minus ma is equal to what's left on the right side is just 1/2 ma. And I'm trying to determine the acceleration. So let me go ahead and get all the A's together. So I'll add ma to the other side, and that will give me 3 halves ma. The last thing I'll do is go ahead and to get a by itself, I'll divide by 2/3 m, or by 3 halves m, which really I'm going to multiply by the reciprocal. So I'll end up with a 2/3. The m's will cancel, and I just have 2/3 g. So we know that the unrolling toilet paper was going to go slower. We know it was going to land last, but now we have an expression for the acceleration. It should be 2/3 the gravitational acceleration. So now we know really how slowly it's going to go. And we could even use this to predict how much later it would take to land, or how much longer. Okay? There's one more that I'd like to do, and that is imagine holding a meter stick like the one I have here, but if I'm holding it at the end and I have a nice little pivot attached so that I could just drop the meter stick and allow it to rotate from that pivot. So I'm going to hold it horizontally, and I'm going to let it go, and it's going to rotate around the end of the end axis where I have that pin. Okay? What I'd like to know is, what is the initial acceleration at one end of the meter stick? So you've got your meter stick. That was a really bad drawing. I'm sorry. Sometimes the orientation is difficult here when I'm writing on my pad. But I have a meter stick that is held horizontally, and the rotation axis is right through one end of the meter stick. And I want to know what would the acceleration be right here initially? And if I were to actually put an object on top of the meter stick, how would the acceleration of the object compare to the rotating meter stick? Okay, so if you want to try to do this, very similar to what we did on the last page, doing the sum of torques and sum of forces, go ahead and try that. Pause the video. All right, so let's go ahead and draw a torque diagram. Let's just, this piece that's on the edge, I'm going to just remove that for right now, because really I only want to do the torque diagram of the meter stick itself. So the meter stick has a weight right in the middle of Fg, and that's really it. I mean, there is a force from the pivot here that's holding it up, but we know that's not causing a torque because it has no lever arm. I am holding the edge of the meter stick before I just release it and let it fall. So this is the moment that I let go and it starts to rotate. So it is Fg at, well, that's not the entire length of the meter stick. That is only L over 2 from the pivot. So the perpendicular distance of R to the force of gravity is just L over 2, and that should equal I alpha. So that is the net torque is equal to I alpha. And I could also say that, let's see, the moment of inertia, because it's a rod rotating about its end, would just be 1/3 ml squared. And I could relate the angular acceleration of the entire rod to the acceleration at this particular point. So I know that A is equal to alpha r, and how far is this object from the rotation axis? That's just a distance of L. So I could replace alpha with A over L. The linear acceleration of this point on the rod or on the meter stick is related to the angular acceleration by the distance to the rotation axis. So, sorry, I have alpha here, which I'm going to replace with A over L. So 1/3 ml squared times A over L. And I can do some cancellations like I did in the last problem. I can cancel that L with one of those on top, and then I have an L on the other side that I can cancel. And I just have mg over 2 is equal to 1/3 ma. If I want to get m by itself, I can go ahead and cancel those masses. And if I were to multiply by 3 to get rid of that 1/3, I have 3 halves g for the acceleration. So that's an interesting result, that the end of the rod that's a distance of L away from the rotation axis is actually accelerating greater than free fall. So if I did have an object sitting on top of the meter stick and I let go of the meter stick and it starts to rotate downward, the meter stick would actually pull away from the object that's in free fall because it's accelerating greater at this point. Now, as you move down the meter stick towards the pivot, each point on the meter stick has the same angular acceleration, but as you get closer to the pivot, they would have smaller and smaller linear accelerations. So where on the meter stick do you think the acceleration is g? And I'll give you a hint. It's not right at the center of mass. So go ahead and try that one. Reach out to me and give me the answer that you come up with. But I want you to determine where on the meter stick would the acceleration be g. Okay, so that should be it for moment of inertia and Newton's second law, the rotational version. Thank you for watching.